The assembly of the B83 strategic thermonuclear bomb begins with the fabrication of its most critical component, the primary pit. The furnace chamber is hermetically sealed to prevent any atmospheric contamination during the casting phase. Atmospheric pressure is evacuated, creating a pure vacuum environment to eliminate oxygen and nitrogen impurities. Electromagnetic induction coils are activated, generating intense heat directly within the material's core. As the temperature climbs, the high-purity material reaches its transition point and begins to liquefy. Complete liquefaction is achieved, allowing for the uniform distribution of the isotopic structure. Minor surface impurities are naturally separated through the vacuum-induced buoyancy of the melt. Automated skimming processes ensure that only the purest material remains for the final cast. With the material purified, the crucible is positioned for the precision pour into the primary pit mold. The liquid metal is poured in a controlled laminar flow to eliminate air pockets and internal voids. The primary mold is filled to capacity, ensuring a dense and symmetrical core structure. The solidification phase begins with temperature sensors guiding a gradual thermal descent. Precision thermal stabilization prevents the formation of cracks or structural weaknesses during cooling. The vacuum is released and the chamber is pressurized with inert gas to facilitate final cooling. The mold is opened, revealing the precision cast core now solidified into its initial spherical geometry. The raw primary pit is successfully extracted, ready for the high-precision machining and polishing stages. Phase 2 begins with the secure placement of the lithium 6-deuteride ingot into the precision milling cradle. Hydraulic clamps apply uniform pressure to ensure zero movement during the high-speed machining process. Calibration continues along the y-axis to define the precise center of the secondary assembly. The spindle reaches operational velocity as coolant flow is established to manage thermal expansion. Rough cutting commences, stripping away the outer layers to reveal the core cylindrical geometry. The machine utilizes its multi-axis capability to shape the sidewalls of the secondary stage components. The internal cavity is machined to house the fusion ignition components with micron-level tolerances. The trunnion table rotates, allowing the machine access to the transverse surfaces of the assembly. Complex parabolic geometries are carved to ensure the proper focusing of radiation within the secondary. The components undergo ultrasonic cleaning to remove all microscopic debris and cutting fluids. Laser micrometers perform a non-contact dimensional inspection to verify the geometry against the master Kiad model. Final polishing ensures the secondary stage components meet the strict reflectivity standards for the radiation case. The uranium-235 pusher is visually inspected for any surface anomalies before final staging. With machining complete, the secondary assembly is sealed in an inert environment for transport to the main assembly floor. The assembly of the aerodynamic casing begins with the precise positioning of the primary titanium nose cylinder. Laser alignment systems verify the structural center point of the forward bulkheads to sub-millimeter tolerances. Initial tack welds secure the forward assembly, forming the foundation of the bomb's supersonic airframe. The casing is rotated at a constant velocity to ensure a uniform circumferential weld bead around the entire diameter. Specialized transition rings are integrated to bond the titanium nose section with the stainless steel mid-body. Non-destructive ultrasonic testing is performed immediately to ensure full weld penetration and structural integrity. Internal structural ribs are fitted to provide the necessary rigidity for high-G maneuvers during supersonic flight. The central structural sleeve is hydraulic pressed into place, creating a multi-layered shell capable of withstanding extreme pressure. Precision ports are plasma cut into the airframe to allow for the integration of the weapon's arming and firing components. Controlled nitrogen cooling is applied to prevent thermal distortion of the alloy's crystalline structure. The exterior seams are ground down to a mirror finish to minimize aerodynamic drag at Mach 2 speeds. The rear structural bulkhead is docked, sealing the main internal volume of the aerodynamic shell. Protected wiring conduits are installed along the casing walls to connect the nose sensors to the rear firing mechanism. Mounting points for the tail fins are precision drilled into the reinforced titanium aft section. Aerodynamic fairing rings are fitted over the joints to ensure laminar airflow across the bomb surface. A specialized thermal-resistant coating is applied to protect the airframe from friction-induced heat during high-speed delivery. A final 3D laser scan confirms the casing's aerodynamic profile matches the digital twin specifications perfectly. With the aerodynamic casing complete, the shell moves forward to receive its internal nuclear physics package. We begin Phase 4 at the electronics assembly station, where the brain of the weapon begins its integration. Precision placement of radiation-hardened processors ensures the firing sequence remains stable under extreme environmental stress. Automated microsoldering links the primary signal bus with microscopic accuracy, eliminating the possibility of human error. Fiber optic lines are integrated to provide electromagnetic interference resistance, shielding the logic gates from external pulses. The board is encased in a dielectric potting compound, protecting sensitive electronics from kinetic shock and moisture. Dual thermal batteries are mounted, providing an independent, high-amperage power source that remains dormant until deployment. The high-voltage controllers for the bridge wire detonators are wired, bridging the logic system to the explosive lenses. Electromagnetic pulse shielding is finalized, encasing the safety system in a protective cocoon of mu metal. Final verification of the safety circuits jar confirms zero leakage and absolute isolation of the firing charge. With the firing circuitry secured and sealed, the electronic heart of the B83 is ready for integration into the physics package. Phase 5 initiates with the preparation of the dual-stage neutron generator, the critical component for timing the fission start. The precision alignment manipulator descends calibrated to sub-micron tolerances for the upcoming integration. Carbon fiber grippers secure the unit, ensuring no surface marring during the high-stakes transfer process. Lifting from the sterile staging area, the generator begins its journey into the heart of the B83 architecture. Inspecting the gold-plated contact pins, each one essential for the microsecond timing of the initiation pulse. The unit is moved into position over the primary stage assembly, maintaining perfect horizontal stabilization. Laser guidance systems activate, projecting a coordinate grid onto the internal mounting port. Slow descent begins. The timed initiation system is designed to interface with the primary pit's high-explosive lens array. Micro adjustments correct for atmospheric pressure and gravitational pull within the assembly chamber. Initial seating is achieved. The physical connection between the generator and the initiation system is now established. Automated probes verify the three-dimensional coordinates to ensure the neutron flux will be perfectly centered. A secondary alignment check ensures the timing pulse will reach the secondary stage with zero latency. The fiber optic umbilically, the digital backbone of the initiation sequence, is prepared for final connection. Connection established. The generator is now integrated into the bomb's firing circuit and command logic. With the integration complete, the manipulator retracts, leaving the core components of the initiation system in place. Internal diagnostic checks confirm the generator is online and awaiting the synchronization signal from the aircraft's computer. Phase 5 concludes. The B83 moves forward one step closer to becoming a fully functional strategic deterrent. The robotic assembly system initiates the configuration of the implosion array by selecting the first high-explosive lens segment. Vacuum sensors confirm a secure grip on the explosive component, ensuring zero slippage during the high-precision transfer. Each lens is handled with extreme care to maintain the integrity of its geometric shape, vital for a uniform shockwave. The arm rotates toward the central primary assembly, guided by a sub-millimeter coordinate system. The first segment is locked into the lower hemisphere of the implosion system, forming the base of the symmetrical array. Precision machined edges allow for a near seamless fit between the explosive blocks, critical for wavefront timing. Laser verification ensures the gap between segments does not exceed 5 microns. Dual arm coordination accelerates the assembly while maintaining the delicate balance of the spherical structure. The lower half of the implosion system takes shape resembling a complex geometric puzzle. A conductive interface is applied to ensure grounding across the explosive array, preventing static discharge. The completion of the lower hemisphere provides the foundational geometry for the explosive lensing effect. Detonator harnesses are secured to the frame, ensuring that the firing signal reaches all points of the sphere simultaneously. Non-destructive testing confirms the absence of air pockets or structural flaws within the explosive segments. With the lower array configured, the system is ready for the integration of the primary pit and the upper explosive housing. Conductive adhesive is applied to maintain electrical grounding across the high-vibration airframe. Data connections are established using gold-plated pins to prevent oxidation and signal degradation. Each mounting screw is torqued to exact specifications to withstand the forces of supersonic release. Fiber optic lines are integrated to facilitate lightning-fast communication between the sensors and the firing logic. Thermal shielding is applied to protect the sensitive avionics from the heat generated during atmospheric friction. The system is powered on initiating the self-diagnostic sequence for the integrated sensor suite. Simulated altitude tests verify that the radar altimeter correctly tracks the descent profile. The pressure sensors are calibrated within a vacuum chamber to simulate high-altitude deployment conditions. Fine-tuning the radar pulse emitter ensures the signal remains clear against ground clutter. The airburst logic is verified, confirming the system's ability to trigger at the precise preset altitude. The calibrated sensor package is physically and logically integrated into the primary detonation control system. An airtight seal is established to prevent moisture or pressure leaks from interfering with the electronics. A vibration stress test ensures that no sensor components will shake loose during the bomber's flight. Safety wires applied to all critical fasteners, providing a mechanical fail-safe against loosening. With final signal validation complete, the detonation control system is certified for the next phase of assembly. The deceleration sequence begins with the inspection of the Kevlar ribbon chute engineered to withstand supersonic deployment. Each ribbon is meticulously packed into a reinforced canister to ensure a flawless deployment at low-level delivery altitudes. Mechanical alignment of the chute attachment points is critical for maintaining aerodynamic stability during the descent phase. The high-strength straps are secured to the bomb's primary frame, designed to absorb the massive G-forces of the chute opening. Electronic testing of the solenoid release ensures the parachute lid will eject within milliseconds of the command signal. Focus shifts to the forward section where the thermal protection system is integrated to guard against atmospheric friction. The surface geometry of the nose cone is laser scanned to ensure sub-millimeter precision before the coating application. A plasma spray application applies the initial layer of thermal-resistant ceramic designed for Mach 2 survival. This composite bond creates a shield capable of dissipating extreme heat during high-speed, low-altitude release. Laser curing instantly hardens the coating, ensuring the material remains intact under maximum aerodynamic pressure. Automated rotation allows for a seamless 360-degree application of the ablation material across the entire forward assembly. A secondary ablation layer is added to provide sacrificial cooling, which protects the physics package from thermal soak. Polishing the surface reduces drag and prevents localized heating at the tip during supersonic flight. Internally, a shock-absorbing honeycomb structure is fitted to protect the sensitive electronics from high-impact shock. The layers are compressed to precise specifications, creating a rigid yet energy-dissipating internal framework. The nose cone is permanently mated to the main chassis, completing the aerodynamic profile of the weapon. A final thermal scan verifies the integrity and uniformity of the heat-shielding layers across the entire surface. The unit enters the shielded inspection chamber, where the internal architecture will be verified against microscopic design tolerances. An automated gantry initiates a 360-degree scan of the forward aerodynamic structure. Non-destructive testing confirms the structural integrity of the honeycomb shock absorption layers. The complex safety systems and PAL circuitry are scrutinized for any microscopic soldering irregularities. Software algorithms verify the spatial coordinates of the internal components to within a fraction of a millimeter. We transition to the rear assembly, inspecting the high-strength Kevlar ribbon chute housing. The automated inspection cycle concludes with a total system certification, confirming the weapon is mission-ready. The certified B83 is carefully lifted for transition into its specialized transport container. The unit is placed into a custom-engineered radiation-shielded transport vessel for secure movement. Shock-absorbing mounts are engaged to protect the delicate physics package from transport vibrations. The heavy-gauge lid is positioned, sealing the weapon within its high-security environment. Manual verification of every seal and bolt ensures the container is airtight and tamper-evident. Serialized security seals are applied, establishing a chain of custody that will remain unbroken until deployment. The transport unit is transferred to an automated guided vehicle for transit to the strategic storage vaults. The weapon travels through the reinforced subterranean corridors of the National Laboratory. The B83 arrives at the secure staging area, awaiting transfer to the Air Force's strategic bomber fleet. The final stage begins in the high-security underground storage vaults, where the B83 awaits its mission-ready certification. Monitoring the long-term integrity of the tritium gas reservoir is essential for boosting the primary stage during detonation. Encasing the bomb in a radiation-shielded transport container for secure movement from the vault to the strategic airfield. The weapon arrives at the aircraft, where the stealth platform prepares to receive its strategic payload. Precision alignment is critical as the pylon loader maneuvers the 2,400-pound weapon into the aircraft's internal carriage. mounting the B83 onto the heavy-duty pylons, a physical union between the delivery vehicle and the nuclear deterrent. The digital vital interface cable is secured, establishing the vital data link between the aircraft and the bomb's internal logic, synchronizing the weapon's digital interface with the aircraft's mission computer for seamless target coordinate uploading. Strategic target data and flight parameters are injected into the weapon's guidance system in real time, simulating the gravity drop sequence, ensuring the fin stabilization system is responsive for high-altitude release. Testing the retarded delivery mode, verifying the parachute system that allows the bomber to escape the 1.2 megaton blast zone. Performing a final security sweep of the dual-key arming system, the ultimate safeguard of nuclear command. Encrypted firing codes are verified, completing the final logical handshake for the strategic deterrent. A final visual inspection of the specialized nose cone designed to withstand the extreme friction of supersonic release. The weapon is now fully integrated, hidden within the belly of the stealth bomber, ready for immediate deployment. The aircraft moves to the runway, a silent sentinel carrying the most powerful gravity bomb in the national arsenal, ensuring the permanent readiness of the B-83 as a cornerstone of the strategic nuclear deterrent. Mission ready.